With a Comet scheduled by British Overseas Airways Corporation to start the world's first jet passenger air service, a few minutes ago I boarded the Comet, together with other passengers making the trip to Johannesburg.
Welcome to the Havilland Aircraft Museum. We are standing in front of the only surviving fuselage from a Comet 1A. You can tell it's a Comet 1A with the distinctive square windows.
We're going to look at the pioneering work that de Havilland did, getting that first jet airliner into service. We're also going to look at how they overcame the chaos resulting from the crashes of the 1950s and how that led to a better understanding of airframe stresses and a better Comet later on.
We're going to look at the groundbreaking work undertaken to develop this incredible aircraft that revolutionized jet commercial travel.
In 1943, de Havilland was looking ahead to the post-war world and the likely needs for the passenger aircraft industry. Ronald Bishop, the designer of the Mosquito, was instrumental in the conception of the Comet jetliner. It was already envisaged that it would be jet-powered and fly at 40,000 feet and in excess of 400 miles an hour. High-altitude flight would make for a more comfortable passenger journey above weather turbulence. The higher cruise speeds led to a swept wing profile of 20 degrees. For ease of training and fleet conversion, de Havilland designed the Comet's flight deck layout similarly to that of the Lockheed Constellation, an aircraft that was popular at the time with many airlines such as BOAC. The cockpit included full dual controls for the captain and first officer, and a flight engineer controlled several key systems including fuel, air conditioning and the electrical systems.
Here we are in the cockpit of the Comet 1A. What are the benefits of this cockpit? What is revolutionary about it?
One of the most obvious changes is the introduction of hydraulic controls. What this meant was that the pilot had the same feel on the controls irrespective of the speed. And this prevented overstressing of the airframe, and it gave the pilot a much better feel for how the aircraft was behaving.
Several hydraulic systems were included on the Comet, run by siphoning power from the 4 Ghost Jet Engines. Operational redundancy was engineered into the aircraft as the systems would still function with only one engine operating. Diverse geographic destinations with varying temperatures and high cabin pressurization on the Comet demanded the use of alloys, plastics, and other materials new to civil aviation to meet certification requirements. The Comet's thin metal skin was composed of advanced new alloys and was both riveted and chemically bonded using redux, a compound developed by de Havilland which saved weight and reduced the risk of fatigue cracks occurring. In July 1949, the Comet made its first test flight, and by January 1952, it had gained a certificate of airworthiness. In May 1952, the first commercial jetliner flight took off from London to Johannesburg, and in its first year in operation, Comets carried over 30,000 passengers. Flights on the Comet were about 50% faster compared to advanced piston engine aircraft at the time, such as the Douglas DC-6, which was capable of about 315 miles an hour, whereas the Comet was at around about 490 miles an hour. In 1953, the Comet had achieved success for de Havilland. Popular Mechanics wrote that Britain had a lead of 3 to 5 years on the rest of the world in jetliners. A slightly longer version of the Comet 1, with more powerful rolls-royce Avon engines, was being developed. This was destined to be the Comet 2. Autumn 1952 saw a Comet fail to take off from Rome Airport runway, and another takeoff failure at Karachi in early 53 were both attributed to pilot error, and some adjustments were made to limit the chances of over-rotation occurring, leading to a wing stall. In May 1953, another Comet was lost in Calcutta at takeoff, and this was attributed to a severe thunderstorm. It was probably pilot error over compensation in the poor weather conditions. These 3 incidents, however, gave no indication of what was about to befall the Comet in 1954. In January, a Comet crashed off Elba in the Mediterranean. All 35 aboard died. A large proportion of the wreckage was recovered by the Royal Navy, And whilst investigations were ongoing, in April 1954 another total loss occurred in the sea near Naples. The entire Comet fleet was grounded.
In less than a year after coming into service, the Comet's fortunes came crashing down. We'll discuss the reasons why. Was it the square windows, or was it something else?
Behind us is the actual fuselage skin from the test Comet that was tested in Farnborough in 1954 to identify the cause of those crashes.
We'll discuss the work undertaken to find out the causes of the two fatal crashes that occurred earlier that year.
In October of that year, a court of inquiry was established, chaired by Lord Cohen, to discover the cause of the crashes. Not only do we have the last surviving Comet 1 fuselage intact at the museum and the fractured failure test section, but also a copy of the report findings into the crash. De Havilland were fully involved in assisting the investigation into the tragedies and worked closely with the Royal Aircraft Establishment at Farnborough. BOAC donated an airframe for water tank pressure tests at Farnborough. The most likely explanation was felt to be fuselage decompression and breakup. Once wreckage was found, other potential causes were eliminated, such as over-rotation stall and engine failure. When flying at 40,000 feet, the pressure difference across the hull skin, allowing for an internal pressurisation of about 8,000 feet, is around 8.5 pounds per square inch. This figure was known as P. The pressurisation and depressurisation was repeated thousands of times at the test tank at Farnborough until the fuselage failed. The fuselage had withstood loads of up to 11 pounds per square inch, 30% higher than required, with no problem. However, once strain gauges were fixed across aperture corners, pressures of up to 43,000 pounds per square inch were recorded. These figures were completely beyond anything believed realistic at the time. These results from Farnborough would be key to the inquiry being able to offer a properly considered judgment on what had happened and decide whether the crashes were avoidable, and given the knowledge at the time, make recommendations for future aircraft manufacture.
This test section helped us to identify the cause of the crashes.
So if you look closely, here we've got the rivet holes where those rivets were put in place, and there's a small tear there. That was as a result of those rivets being punched through and not drilled. As a result, a small amount of additional strain that propagated through the entire fuselage.
The first Comet to crash off Italy was largely recovered, and when assembled, the failure point was in the roof behind the cockpit where the ADF, that's the automatic direction finding windows, were. The second aircraft failed initially around the rear escape hatch window. The shape of the windows is not relevant as they are spheroid in shape, and in fact the window shape of a Comet 1 is within 5% radius of a Boeing 737. Subsequent Comet models had oval windows as the rivet technique was abandoned and the windows were redux bonded. It also served the purpose of addressing the public anxiety about flying in a plane with square windows. Did the inquiry conclude that de Havilland were culpable for the aircraft crashes because of defective design and testing? And we have a copy of the report here at the museum, and the findings tell us a lot. It says that de Havillands were proceeding in accordance with what was then regarded as good engineering practice. The pressure testing of the cabin was able to tolerate nearly double the P figure, but at the time the corner stress amplification was not fully understood. It also appears that the stress testing de Havilland had done prior to the Comet's launch might inadvertently have strengthened the fuselage structure of the test specimen. So getting a true result for an aircraft in service was invalidated. The inquiry concluded a combination of square windows and rivet fastening techniques were to blame.
At least de Havilland were not deemed negligent in this case. They'd fulfilled all of the testing that was required at that particular time.
The Comet. Powered by 4 Rolls-Royce Avon jets, its takeoff run is exceptionally short. Let's go upstairs and get alongside the Comet in the air.
We're sitting in the flight deck of the Comet 4. This is the final version of the Comet that entered production. We're going to consider the later marks of the Comet, following the investigation on all the redesign work, how that contributed to a very successful airliner, and how it also contributed to other airliners gaining the benefits from all the work that had been done by de Havilland.
The Comet 4 made its first commercial flight in 1958 and was directly derived from the Comet 3, which was used as a test airframe to speed up airworthiness certification. The Comet 4 was a larger aircraft powered by significantly better Rolls-Royce Avon engines and could carry up to 81 passengers. The thicker gauge construction of the cabin metal, alterations to stress points on the cutouts and rivet points meant that this was now a very different aircraft. The years that the Comet was grounded had allowed competitors to catch up, particularly Boeing, which launched its 707 in the autumn of 1958. The Comet 4 had much improved range, being able to fly London to New York, and with the Boeing being more cost-effective for many airlines, it proved very stiff competition for the new de Havilland aircraft. The Comet 4 sold just over 70 units and continued in service until the early 1980s with Dan Air. De Havilland continued passenger jet aircraft design and development after the Comet, with the Trident and the Hawker Siddeley 146, both of which can be seen at the museum. Commercial passenger aviation owes a massive debt to the pioneering Comet, as the findings after the tragic crashes enabled the aircraft that followed to be tested in more appropriate ways. This had a huge impact on safety, comfort, endurance and cost, and ultimately led to the international travel industry we see today. As a footnote, we mustn't forget the Nimrod, developed in the mid-1960s from the Comet 4. 50 of these aircraft served in various guises from 1967 until 2011, offering maritime patrol, surveillance and electronic countermeasures technology of the highest order. Powered by Rolls-Royce Spey engines, the Nimrod was capable of 580 miles an hour and had a range of up to 5,700 miles. During the Falklands War of 1982, a Nimrod flew over 8,000 miles on one mission with in-flight refueling. Once the fuel weight had dropped later in the mission, the aircraft could shut down 2 of its engines to again increase its endurance.
The use of reverse thrust enables it to operate from quite small.